Good evening. Welcome to the 30th programme of Astronomy in Space. In this month's programme, we are going to be looking at the first stars and galaxies that formed in the universe soon after what astronomers call the Big Bang. The most intense bursts of starbirth are thought to have occurred in the early universe in massive bright galaxies. These starburst galaxies convert vast reserves of cosmic gas and dust into new stars at a furious pace, many hundreds of times faster than in grand galaxies like our own galaxy, the Milky Way. By looking far into space at galaxies so distant that their light has taken millions of years to reach us, astronomers can observe this busy period in the universe's infancy. In March 2013, a team of astronomers led by Maruša Predak, a professor at the University of California, first discovered these distant and enigmatic starburst galaxies with the American National Science Foundation's 10-meter South Pole Telescope, a radio telescope built in 2007 at the Armiston Scott Station in Antarctica. Then, Professor Maruša Predak used the European Southern Observatory's radio telescope array in the Atacama Desert in Chile to zoom in on them to explore the formation of the first stars in the young universe. The team was surprised to find that 40 of these distant dusty star-forming galaxies are even further away than expected. This means that on average their bursts of star formation took place 12 billion years ago, when the universe was just under 1.7 billion years old, a full billion years earlier than previously thought. Two of these galaxies are the most distant of their kind, so distant that their light began its journey when the universe was only 1 billion years old. A few days ago, Professor Maruša Predak and her team published a paper about their newest find. She has now broken her own record to discover a galaxy in the early universe that is just 13 billion years old. Maruša and her team made the discovery using an advanced spectroscope fitted on the 10-meter Keck 2 telescope on the summit of Mauna Kea in Hawaii. It was made possible through a phenomenon predicted by Albert Einstein, in which an object is magnified by the gravity of another object that is between it and the observer. Astronomers call this a gravitational lens. In this case, the detected galaxy behind the galaxy cluster was MACS 2129, which is massive enough to create 3 different images of the object. Our universe came into being 13.7 billion years ago in what has become known as the Big Bang. We can never look back to see the moment of creation in any one direction because we are in the middle of it and the remnants of the Big Bang are all around us. After the initial inflation period, the universe has continued to expand, so a galaxy which sent its light 13 billion years ago is now over 40 billion light years distant from us. The so-called observable universe is over 92 billion light years in diameter, and we have no idea what lies beyond. To be able to observe the universe after the moments of creation, we are going to need a really big telescope, and to see through the dust and gas hiding it from view, it would also need special infrared vision. The ELT is designed to make detailed studies of the first galaxies and to follow their evolution through cosmic time. Observations of these early galaxies will give us clues that will help us to understand how these objects form and evolve. The James Webb Telescope, now under construction, is the next generation space observatory. It has a 6.5 metre mirror that will provide remarkable sensitivity from long wavelength orange-red visible light through near-infrared to the mid-infrared, and it is the successor instrument to the Hubble Space Telescope and the Spitzer Space Telescope. A large sun shield will keep its mirror and 4 science instruments below -220 degrees centigrade. One special study with the telescope involves observing some of the most distant objects in the universe beyond the reach of existing ground and space-based instruments. This includes the very first stars during the age of what astronomers called re-ionization and the formation of the first galaxies. Another goal is to understand the formation of stars and planets. This will include imaging molecular clouds and star-forming clusters. Our Earth is an exceptional planet that is teeming with life and is home to us humans. We are fortunate to be orbiting around a steady star, the Sun, in a relatively warm, habitable region of the solar system that enables life to flourish. As Professor Carl Sagan reminded us so many times, we are all made of star stuff cooked up inside the first stars. The requirement for the existence of life were all met by the time our Sun was formed. Our galaxy, the Milky Way, is a huge island of 400 billion stars laid out in the form of a spiral. Its size is so huge that travelling at the speed of light, it would take a space traveller 150,000 years to trek across the galaxy from one side to the other, which is a very recent estimate. I made a program all about this in May 2015, called Galactic Whirlpools. The Milky Way is about 2,000 light years in thickness, and our Sun and planets lie at a safe distance of 26,000 light years from the galactic centre. Any elements heavier than hydrogen and helium inside stars are defined in astronomy as metals. The stars in our galaxy fall into 2 groups. Population 1, or metal-rich stars, are young stars with the highest metal content in their composition. Our Sun is an example of a metal-rich star. Population 2, or metal-poor stars, are those with relatively little metal. These stars were formed during an earlier time of the universe. Intermediate population 1 stars are common in the bulge near the centre of our galaxy, whereas population 2 stars are found in the galactic outer regions of the galaxy, the galactic halo, which are older and more metal-poor. Globular clusters around our Milky Way contain high numbers of population 2 stars. Astronomers have long theorized the existence of a first generation of stars known as population 3 that were born out of the primordial material from the Big Bang. All of the heavier chemical elements such as oxygen, nitrogen, carbon and iron, which are essential to life, were forged in the centres of stars. This means that the first stars must have formed out of the only elements to exist before today's stars: hydrogen, helium and small amounts of lithium. These population 3 stars would have been enormous, several hundred or even 1,000 times more massive than the Sun, blazing hot and exploding as supernovae after only 2 million years. Until recently, the search for physical proof of their existence had been uncertain. Then, in 2015, a team of astronomers led by David Sobral from the Faculty of Sciences of the University of Lisbon in Portugal and the Leiden Observatory in the Netherlands used ESO's Very Large Telescope to look back into the ancient universe to a period known as reionization, about 800 million years after the Big Bang. The team discovered a number of surprisingly bright, very young star-based galaxies. One of these, labelled CR7, was an exceptionally rare object, and by far the brightest galaxy ever observed at this stage in the universe. With the discovery of CR7 and other bright galaxies, the study was already a success, but further inspection provided more excitement. The astronomers found strong ionized helium emission lines in the spectra of CR7, but no signs of any heavier elements in a bright nebula in the galaxy. This meant that David Sobral had discovered the first good evidence for clusters of population 3 stars that had ionized gas within a galaxy in the early universe. Within CR7, bluer and somewhat redder clusters of stars were found, indicating that the formation of population 3 stars had occurred in waves, as had been predicted. What the team directly observed was a last wave of population 3 stars, suggesting that such stars should be easier to find than previously thought. They live among regular stars in bright star-based galaxies, not just in the earliest, smallest and dimmest galaxies, which are so faint as to be extremely difficult to study. The discovery of the bright cluster of young star-based galaxies, including CR7, was a breakthrough in the hunt for the first stars to form in the universe. In May 2016, astronomers at Indiana University announced that they had found a faint blue galaxy nicknamed Liochino, or Little Lion, which contains the lowest level of heavy chemical elements or metals ever observed in a gravitationally bound system of stars. Officially, the Little Lion is named AGC 198691. It is about 30 million light-years from the Earth and lies in the constellation of Leo Minor, the Lion Cub. Alex Herschower and his team obtained a spectra of the single emission nebula region in Liochino with the 4.5-meter multi-mirror telescope on Mount Hopkins at Arizona in America. These observations enabled the measurement of the temperature-sensitive oxygen-3 line, and therefore they were able to observe the direct oxygen abundance for Liochino. The astronomers found this system to be extremely metal deficient, with an oxygen richness of 7, making Liochino the lowest abundant star-forming galaxy known in the local universe to date. Apart from low levels of heavier elements, Liochino is unique in several other ways. A so-called dwarf galaxy, it is only about 1,000 light-years in diameter and composed of several million stars. The Milky Way, by comparison, contains up to 400 billion stars. The conditions in the early universe following the Big Bang were beyond our understanding. Nothing existed before the Big Bang, and time only came into existence at the same moment our universe was formed. What we know is that immediately after the Big Bang, the universe was extremely hot and consisted of a thick soup of various kinds of tiny atomic particles. During the minutes that followed, protons, neutrons and electrons, the building blocks of atoms, formed. The universe then expanded quickly, cooling in the process. The only chemical element that existed up to that point had been hydrogen in the form of protons. After 2 to 3 minutes, the temperature had cooled to 1 billion degrees. The first elements heavier than hydrogen, including deuterium, were formed. From deuterium, the first helium element formed. The collisions of several helium atoms caused the third heaviest element, lithium, to occasionally form in small amounts. The universe was then composed of 3 elements: hydrogen, helium, and lithium. Roughly 75% of the total mass consisted of hydrogen, 25% was helium, and a tiny fraction was lithium. The first phase of element making was complete just 3 minutes after the Big Bang. For life to later evolve in the universe and for humans to emerge, these 3 chemical elements were not enough. The elements needed to sustain life, including carbon, nitrogen, oxygen, and other elements in the periodic table, were still missing. Those were later built up inside stars over billions of years. Only the interiors of stars are hot enough for heavier elements to be continually made from the available lighter elements, such as hydrogen and helium. These stars, and later also galaxies, had to emerge first. For that, the first atomic particles had to combine with the 3 electrons in the universe to form neutral atoms. For quite some time after the Big Bang, these atoms were racing about in a cosmic jumble, and the energy and direction of the photons were constantly being scattered. So, this soup of particles and rays was fairly opaque, resembling a thick fog. About 380,000 years after the Big Bang, the universe had grown so much while cooling down that a fundamental change occurred when it reached a temperature of about 2,700 degrees centigrade. The nuclei and electrons were moving slowly enough by then that the positively charged nuclei could capture the negatively charged electrons to bind them together. The photons that had been flying around since the Big Bang suddenly had much less chance of being scattered, and the universe became transparent for the very first time. At last, the photons were liberated from the electrons and could travel long distances unrestricted. Today we call this the cosmic background radiation. This is a faint leftover glow of the Big Bang from almost 13.7 billion years ago. Since becoming transparent, the universe has grown over 1,000 times larger. The energy density of the cosmic background radiation decreased as the universe volume increased. For that reason, the temperature of the background radiation reaching us today is not 3,000 degrees, but only minus 270 degrees centigrade. As it continues to expand, someday in the far future it will reach absolute zero. A few 100 million years passed before the universe completely changed its qualities yet again. The Dark Ages that had persisted since the atomic nuclei had begun capturing electrons came to an end. The first stars in the universe emerged from the giant and increasingly clumpy clouds of gas. They were composed of just the hydrogen, helium, and lithium of the primordial soup left behind after the Big Bang. In this way, the universe was lit up for the very first time. The ultraviolet light emitted by these stars led to the ionization of neutral atoms in the gas clouds. The intense stellar radiation had dislodged the electrons from their atoms. The very existence of the first stars had therefore altered the conditions for the formation of later stars like our Sun. As a result, star formation continued more efficiently and greater numbers of stars formed, and, together with the gas, they arranged themselves into huge clouds of stars known as galaxies. In their interiors, the first stars made chemical elements heavier than hydrogen and helium. This production of additional elements led to big changes in the universe. From that time on, countless stars began to chemically enrich the surrounding gas in their galaxies. After about 9 billion years, enough of the elements had collected for the formation of our Sun and the solar system. At present, after 13.7 billion years of cosmic evolution, the mass fraction of the element from lithium to uranium is about 2%. When the Sun was born, 4.5 billion years ago, it was about 1.5%. Apart from any lithium, all of this material was produced inside stars. For this reason, the oldest ones are the key to understanding exactly how the chemical mixture now present in the universe developed over time. We next come to Professor Anna Friebel, who is a German astronomer born in Berlin in 1980. She has been working on discovering the oldest stars in the universe for over 10 years. Anna is credited with the discovery of a star named HE 13272326. This star was discovered in 2003. It shines at magnitude plus 13.5 and it lies in the constellation of Hydra, the water serpent. HE 1327 is very remote. It lies about 4,000 light years away. Anna and her team could only detect 4 iron lines in the whole of the star's spectrum. Because of its enormous iron deficiency, the star has almost no iron in it at all. The fairly warm surface temperature further reduced the strength of the lines. Yet Anna found that the iron abundance to be just 250 thousandths of the iron content of our Sun.
To the science. So here is this picture again, this fuzzy blob. This is one of the most important stars we have found. It's, as far as we know, it's a second generation star because its iron abundance and other elements are so deficient that only one first star supernova is required or needed to produce all these elements that we see in the star now. I should say here for clarification, this star is actually really unevolved. It has not even started yet converting anything else but hydrogen to helium in its core. So this star has not really made any heavy elements itself. Whatever we find in the stellar surface today came from the birth gas cloud from which the star formed, which means it must have come from that previous generation star that enriched that gas. Okay? So this is really the pinnacle of our work. I think in the last few minutes, I'd like to introduce this second star to you. Here, another fuzzy blob in the universe. Now, this one's actually fairly bright, so if you have a small telescope at home or you know someone who has, you can actually take a picture yourself. This was taken by an amateur astronomer, and he sent me this picture there. So that's kind of nice, but again, you need that spectroscopic knowledge to say that this is one of the oldest stars we know because we have measured its age. And so what's the big deal here? We have taken a spectrum, and the spectrum was very unusual because it contained absorption lines from very heavy rare earth elements, and that included elements like thorium and uranium. And you hopefully know that these are radioactive elements, so as soon as you deal with radioactive material, you have yourself a clock. So here is why this measurement takes an incredible amount of data, and it's a very difficult analysis because we want to measure the uranium abundance. And so here you have absorption lines: magnesium, iron, neodymium, samarium, iron here. And you see here's a blow up star. So if you look at this blue line, this is a synthetic spectrum that we have created to model the star that contains no uranium. And the question is, does that one correspond to the observed data, which is the dots? And clearly the answer is no. Instead, we have data that's a little bit lower, which means there is a little uranium absorption. And so we have then created models that kind of reproduce this here. If the uranium was not decaying, it would have been absorbed up to here. So that would be easy to measure, but it's good that it's decaying because it gives us this clock. So, but making this measurement here requires extremely exquisite data. But it worked because this star is so bright, and we got an age. Well, this is not precision cosmology, but nevertheless, it's an important contribution to the early universe, or to studies of the early universe, and it confirms that the whole story I have told you about the chemical composition, and that telling us that we can look back in time to this early era by measuring chemical abundances, is actually correct. So here are different element ratios. They all involve either thorium or uranium or both. And these are ages in billion years. Now the universe is 13.8 billion years, so this is just a mathematical number that pops out. Obviously it's unphysical, but math doesn't really care about physics, so we have to take it. But if you average all of this, it comes out to about 13 billion years, and that is the number we like. It's very consistent with the age of the universe. Now there are some uncertainties, of course, but it is not 10 and it's not 5 billion years. It's not like the sun, and even 10 is still a while away from 14 here. So the concept of stellar archaeology is correct. It works. And these old stars here, first of all, they really are old, and we can use them to explore the early universe.
The new generation of telescopes will help astronomers better understand the formation of the first stars and galaxies, and the evolution of the universe. First up, in 2018, will be the James Webb Telescope. It will be launched into orbit on an Ariane 5 rocket from the European spaceport near Kourou, French Guiana. The telescope's 4 instruments, cameras and spectrometers, have detectors that are able to record extremely faint signals. One instrument, NIRSpec, has programmable micro-shutters which enable observations of up to 100 objects simultaneously. Astronomers working together with the new extremely large telescope in Chile, which should be operational by 2026, and the James Webb Telescope, will be better equipped to understand the origin of the universe far better than ever before. So there are more exciting discoveries yet to come. That brings this month's programme to a close. Thank you for watching. Please visit our website, Astronomy and Space Blogspot, where you can watch all of our past shows. And if you like this programme, please share it with your friends and members of your local astronomical society. All of our programmes are free to watch, so please follow us on Vimeo or subscribe with us by adding your email address on the top right of our website so you never miss a monthly show. Until we come back next month, good evening.